In this one, let's explore why the domain of the natural log function is greater than 0. So I'm not going to just graph the function and take it from that perspective, because we want to answer the question why. We really want to understand where, for example, the natural log function comes from in the first place. So we got to return to a simple mathematical object called a exponential function with base e, where e is about 2.718. Now there are a lot of videos on YouTube that explain the origin of the value of e, which is again about 2.718. So here I'm just going to remind you of the graph of e to the x. So let me just quickly show you what that looks like in practice. Alright, so let me move myself aside, and I'm going to graph e to the x. So that's this yellow graph that has just appeared. Now on this graph, let's mark some points. So for example, when 0 goes in, 1 comes out, seems like. So let's mark that as a point. So 0 in, 1 out, okay? Maybe let's label that. So you see it's the point 0, 1 right here. Let's add some additional points for emphasis. So let me just do that right now. I'm going to do, for example, when negative 1 goes in, e to the negative first comes out. So that's this point right there. Now it looks like e to the negative first is about 0.368. That's a value, it's just a number. Negative 1 goes in, that number comes out, no problem. Now, we want to study what happens over here as I move in this direction. Something goes on there. We got to really zoom in on that part of the graph. So let me just scoot over this way. Now look, here where I am, it looks like there's a gap between the graph and the horizontal axis. Then as you scoot over in this direction, it looks like the graph and the horizontal axis basically touch. But is that really the case though? Well, take a look. The best way to understand this is just to zoom in. Just zoom in to a very fine level of detail. It's really helpful here. And take a look. As you do this, you see what's happening here? You see what's happening? Now this gap has actually grown. I can kind of fit within it, so to speak, between the horizontal axis and the graph, right? I can kind of fit in here. The point is now there's a big gap here. So the graph and the horizontal axis are not really touching anymore. See? So when graphs, for example, appear to touch an axis, it's just because you haven't zoomed in enough. Take a look. Let me scoot over to the left pretty far now. Look, and I'm trapped within this gap here the entire time. And this gap is not going away. Now, it's true, look, because this is right here under me, negative 7.739. This is just negative 7.74, negative 7.41. So I'm going in very tiny increments, right? But it's zoomed in, so it seems like it's big, but it's actually not, because this is negative 7.47, this is negative 7.748, and so on. Just keep that in mind, you see? So the gap is present. Let me zoom back out now, and you see, and kind of scoot over this way, very far to the left. I'm going kind of far to the left. I'm going to zoom out, okay? And I'm going to go way far to the left. This is just a purely visual exploration of what happens with these graphs, okay? Look, I've gone all the way to, let's see, about negative 10.5. Again, as an artifact of the zoom level, it seems like the graph and the horizontal axis are touching, but are they really touching? So take a look here. What you have to do now is just zoom in and just keep zooming in. Okay, keep zooming in, and once you've done that enough, you discover pretty quickly that again, at negative 10.5 between the graph, the yellow line, and the horizontal axis is again a gap. What is this telling us as a story? It's telling us that the horizontal axis is the horizontal asymptote for e to the x. In other words, the graph approaches it and it gets ever more close to it, but it doesn't cross it. That's the idea here, okay? So we can indicate that by something like, for example, y equals, and then you put 0. And you just graph that. So right now you see I've made it pink. It's convention to mark horizontal asymptotes, vertical asymptotes likewise, but here we're dealing with horizontal ones, to mark them with dashed lines. So let me just dash this line a little bit so you can see for yourself, okay? All right, and I perhaps should make it a bit thicker too. So let's see. Let's make this 4. Okay, 5. There you go. So as you can see now, it's like a dashed pink line. It's the horizontal asymptote. This gap can be made as small as we want as we go to the left, but it never disappears. So now comes the next stage in the process. Let me do my default zoom level. This is the default zoom level. And again, here it looks like this now. What I'm going to do is add some additional points. Then we're going to look very carefully at where those points go when we mirror across y equals x. Okay, so I'm going to add a point, for example, like -3 and then e raised to the -3rd. Okay, that's my point. All right, I'm going to add a label to it. So right below me it says when -3 goes in, 0.05 about comes out. Let's do one more at, say, -4, okay? So I'm going to do here, let's see. When -4 goes in, I'm going to have e to the -4 come out. That's just a number, after all. Let me label it. So that's this value right here. -4 in, 0.018 out, okay? Good. Now what we are going to do is mirror across y equals x, because that is the standard procedure for generating the mirror image, in other words, the inverse function, and the log function, ln function, which is like a log base e, in other words, the ln function is the inverse of e to the x. Look very carefully at what happens here. So I'm going to begin by also, you know what, I will add one more point. So like this is x equals 1, so I'm going to punch that in and get another point on the graph. So let's do that. I'm going to have 1 and then in, and then e to the first will come out. And then label that point. So now we have these points. We want to look at their mirror images across y equals x. Now what does that mean? What it means is the way to do them is you just switch the x and the y. So you see like this point below me has an x value of 1 and a y value of about 2.718, which is the value of e. You just switch those and that gives you a new point. So let me, in other words, mark this line y equals x next. This is y equals x, this line right here, angled. Now let's mirror across it. So in other words, instead of having the point 1, 2.718, I would have the point e, for example, to the first, 1, like this. So that becomes this pink point right below me, you see? It's been mirrored across this line this way. Now what does that mean, mirrored? Let me just zoom in here so you can understand that better, okay? It means that trace my position very carefully, right? The corner here of where my mouse is, right there. That means that the distance from this point to y equals x, that is the same as the distance from y equals x over to this point. That's what we mean by saying we are mirrored. The distance is the same. Okay, so now let's repeat this for a couple other points. Okay, so this is 0, 1. Let's flip those coordinates, and I'm going to make them 1, 0. So now, again, look very carefully. Let me do the label here. The same thing with the other one. So now this is the point 1, 0 in it right here, at the corner of the camera there, or the frame. Now look very carefully. Here's another point, -1, 0.368 about. Let's mirror that across. So in other words, switch. So I'm going to have e to the negative first, and then -1. And what you get from that process is this white point in this position. Now something begins to happen here that we cannot simply ignore. So what is that something? Well, take a look carefully. Okay, let me zoom in right here and trace from -1 up to the graph. That's a vertical distance. Okay, one more time. It's a vertical distance from here to here. That vertical distance, that gap between the horizontal axis and the graph, that comes over here now. So if you look across the top of the frame there where I'm located, from -1 over to the point, now it's horizontal, but it's preserved, you see? So what is, in other words, here, this way vertical, here it becomes the same horizontal distance. Let's do this one more time, okay? So next, I'm going to work with the point, let's see here. Grab another point. I'm going to do -2. So let me just add a point right here at -2. So now -2 goes in. I mean into e to the x at first. And then e to the -2 right here. Okay, let me label that. So that's the point -2, 0.135. Now mirror it to the other side of y equals x carefully. Okay, so let's do that next. So when I do that, I'm going to have e to the negative second, and then negative 2. Now what am I saying there if you listen carefully, right? All I'm doing is I'm switching just the normal order of x and y. That's all I'm doing. So now the mirror image of the point negative 2, 0.135 becomes the point 0.135 comma negative 2. Let me stress this one more time because maybe that's not so easy to see anymore, but the distance from the point negative 2, 0.135 straight perpendicular to y equals x is the same as the distance from y equals x perpendicular straight down to this point right there. Let me stress one more time. Above me, right here, very carefully, right? You see where I am located, there's a gap between negative 2 and the point. There's a gap. That gap does not disappear. So what I mean is, look very carefully. Let me zoom back in over here. See that gap now simply becomes this horizontal gap right there above me. See, now it becomes a horizontal gap between the point and the vertical axis. So what is this telling us? Well, what it's telling us is that, let me zoom back. I'm going to do this one more time, okay? Let's focus now on, let's see, negative 4. So I'm going to add one more point here. So negative 4 comma e raised to the negative 4. Okay? It's just that point. But then I'm going to switch the normal order of x and y. So let me do that right now, okay? So I'm going to do, in other words, e to the negative 4 first. So e raised to the negative 4 first, followed by negative 4. Okay? Now, look very carefully. The same kind of artifact begins to emerge along the vertical axis. So what I mean is, you see how below me that point seems to touch now the x-axis? As if the graph were touching the x-axis. But again, we know that if I zoom in, right here, there is actually a gap present between the graph and the horizontal axis. So now, let's scoot over to here. We're just exploring, okay? You know, kind of zooming through different realities in mathematics. Okay? And now, let me find that point, okay? And then zoom in on this point. Once again, let me emphasize this. I hope you can see it. Below me now, this is the image of that point. So instead of negative 4, e to the negative 4, this is e to the negative 4 comma negative 4. There's now a separation between the vertical axis and the point still. So what is all of this saying? Well, what it's telling us is the following. Okay, let me zoom back out. That the following is true. Whatever gap exists here, whatever gap exists where I'm moving between the graph and the horizontal axis, that gets translated into a vertical gap between the graph of the natural log function and the vertical axis. Now let's think about a reasonable way to describe the vertical axis. How might we refer to it that's useful? Well, it has a characteristic that we use to label it. What do I mean by that? So take a look. For any of these points, okay, look very carefully. I'm going to move only along the vertical axis. Trace, okay? So let's see here. Let me zoom in. There you go, okay? This is negative 3.5 on the y, but x is 0, correct? This is negative 3 on the y, but x is 0. This is negative 2.5 on the y, but x is 0. Right? This is negative 1.5 on the y, but x is 0. Because for every point along the y-axis, the x-coordinate is equal to 0, we can describe the y-axis also as x equals 0 for that reason. We use that characteristic of it, you see? So here, I'm going to say, in other words, x equals 0. It looks a bit yellow at first, so what I'm going to do is, again, I'm going to dash it. Why am I going to dash it? Because I'm going to now treat x equals 0 as a vertical asymptote for the reason that these points that I mirrored across y equals x approach the vertical axis, but don't cross it, you see? So I'm going to dash this right here. So let me just do that right now. Dash it. There we are. Maybe thicken it a little bit, so maybe make it like 5. There we are, okay? So now we have this vertical axis. This is dashed. in yellow there, right? There are gaps always between these points and the axis. It doesn't matter how far down you go, right? Like this point right here, you see there's a gap. Very carefully if you look. It doesn't matter how far down you go, there will always be a gap. As long as you take the time to zoom in closely enough, to a very fine level of detail, you will discover a gap there, okay? So in other words, now I'm going to connect these images of the points of e to the x across y equals x. I'm going to connect those with a curve. We call that the ln vex function, like this. So here it shows up as this white graph that has suddenly appeared. Just told the program to generate it. And now let me zoom in, you see? And now we have this gap right here. And again, let me stress, it doesn't matter how far low you go towards negative infinity, which is where I'm traveling now, towards negative infinity, okay? Actually, I'm stationary, so to speak, and the graph is traveling, right? But you get the idea, okay? Now I'm traveling. You see there's always a gap present. If I zoom in enough, you see that gap is present right there. And that gap never goes away. What is this telling us? It's telling us, friends, lastly, that x equals 0, because we can get close to x equals 0, in other words, the y-axis, but we can never actually reach it, so to speak. It's telling us that the domain of the natural log function is x has to be greater than 0. Not equal to 0, has to be greater than 0 because of the presence of this gap that you see here, and because now the vertical axis x equals 0 is the vertical asymptote. In other words, where does this gap come from? It comes from e to the x being mirrored across y equals x, you see? And you get a nice gap going there that never vanishes, just like the gap for e to the x with respect to the horizontal axis never vanishes. So x greater than 0 then becomes the domain of the ln function. But not only is it the domain of the ln function, it's the domain of log base 2 of x, it's the domain of log base 3 of x, and all of the other basic log functions. I'm going to leave it here. I hope all of this has been interesting to you. Please remember to leave a like, to subscribe. Thank you so much for watching. I will see you in another video.